almost like the first talk is automatic amortized analysis of dynamic memory allocation for lazy functional programs, and it's by Hugo Simões, Pedro Vasconcelos, Mario Florido, Steffen Joost, and Kevin Hammond, and Hugo will give the talk.
Okay. Yeah. So I'm feeling quite an adrenaline rush. Who needs roller coasters at the Tivoli, but you can talk for over 300 people, right? So my name is Hugo Simões. This work was done in collaboration with my colleagues in Porto, St. Andrews, and Munich. I've been working on lazy resource analysis for lazy evaluation for the past 7 years in the context of my PhD, which started about 8 years. At some point, when my PhD grant was over, I considered seriously quitting, having nothing that I thought I could show for. But fortunately, my colleagues Pedro and Steffen teamed up with me, my advisors, and in a bit less than 3 years, we got our results ready and accepted here at the ICFP, and that's what I'll be talking about today. So, as most of you know, predicting runtime calls of an arbitrary, lazily evaluated program is hard. If you try to do it automatically, even more, right? Even on a very simple example like a let, it can be hard to know what the cost is. Under call by value, you can cost the sub-expressions, because you know those will be evaluated. And the call by name or call by need, the introduction and evaluation of the expression are not done at the same point. And moreover, you don't even know whether E1 will be evaluated at all. And also, under call by need, you don't want to cost the same expression more than once. So, we are working with a technique called amortization, which allows us to reason about a sequence of operations instead of, for example, taking the sum of the worst case bounds of each operation individually. So basically, we're looking at the sequence of operations instead of at each operation separately. In order to apply this technique, you find a mapping from configurations to non-negative numbers, and then you ensure that for all transitions, the value of the configuration you have before the transition bounds the actual cost of the transition and the value of the configuration after the transition. If you have done that, then the value of the initial configuration is an upper bound on the overall cost. This work we have focused on costing heap allocations, so our configurations in concrete here will be heap layout. Amortised analysis is a tool from the 80s, which has more recently been applied in several settings in this type-based automatic analysis. So, automatic in the sense that you feed the program to this analysis, and it will either say, sorry, I have no clue, or provide usually a reasonable resource bounds on the metrics you are costing. So our main contribution was developing the first type-based automatic analysis for lazy evaluation. In fact, it's the first automatic analysis for lazy evaluation, and you can find prototype implementation online. Right? We focus on heap allocations, but the approach is general enough to be applied on different resource metrics. So what's the functional language that you can pass to our analysis. Well, it's basically lambda calculus with a recursive length binding, plus a couple of rules to deal with constructors. We have a match, we have a let cons to introduce constructors, and a match to do pattern matching on them. We needed the let cons because we wanted to know when a constructor was introduced instead of to distinguish between introducing a constructor or just using it. Since as I said in the beginning, in a lazy setting, introducing an expression and evaluating it might be at different points. So usually you wouldn't need these in the strict setting, but in the lazy setting we do need. So we developed a cost model based on Cessna refinement of launch tree semantics. We have here an example of the let rule. So how is the let evaluated under this cost model? So if you have a let, you want to evaluate it under a heap, so just a mapping from locations to expressions, to possibly unevaluated expressions. You evaluate E2 on the context of the previous heap, where you allocated a new heap cell and put the expression E1 there with a reference, so that you could access it from either E2 or E1. And if that evaluates to a weekend normal form in a new heap, that's the result you're going to give also in the let. Okay. So this was the semantics. What we did was instrumented it with costs, and the cost we are looking at is the cost of a heap allocations. So in the let, if you notice, the let is one of the points where we actually allocate a new heap cell, and that's cost with one cost, unitary cost. And the let cons would be the other rule where this cost would be introduced. We have the cost model so that we can then compare our analysis to running to what would happen if we ran the program. Sorry about that. Okay, so our analysis is a type-based one. The types you can find in our analysis are type variables, data types, recursive data types, functions, and thunks. Thunks is a new part for this work on callback need. What you, if you remember what here on the left on the let expression, what you put in the heap is a possibly unevaluated expression, and so we give types, thunk types to things that we don't know if are evaluated, might not be evaluated. And so, for example, in the list type, the type of the head and the type of the tail are thunk types because we don't know whether that's evaluated or not. What we have in this type system is annotations then. For example, these P's in the thunk and the functions are the number of heap cells required to execute the function or the func, and the p prime will be the number of heap cells we would get back. The actual cost will be p minus p prime, right? And each constructor is has an annotation that then we can in a type system we can relate these annotations. So key rules in the type system. The let rule, for example, what we do is if we find a typing for E1, Q and Q prime would be the cost notations of E1. What we do is threaten to E2 to the type of X. So X will be a func that will need the Q heap cells to run, for example, right? And then in the overall cost, we add 1, which was, as we've seen, the let always costed 1 heap cell. The let cost is similar, except we know that what we put in the heap is already in wicked normal form, and so the thunk has zero cost. What we do is just take the annotation from the type of the constructor and add it to our costs. This would be a way to use amortization to be able to defer costs laterward. By the way, these two examples are non-recursive, but the full the rules are. One of the key rules is this prepay, that again allows to shift the cost, or shifts when the cost is paid. So for example, we could imagine that in the let, and they're called by value, we could pay for the cost of E1 right at the point where we introduced the let. That would model call by value, or we could simply not use prepay ever, and that would model call by name, because then each use of the variable will trigger the full cost. So we have the inference algorithm takes to build an inference algorithm. We first apply Davis-Miller inference to get an annotated type derivation, decorate the types, traverse it, gathering linear constraints on the relation that we could find in the type rules, and then feed those constraints to an LP solver and get the result with the types annotated with actual values. So I'm going to show you an example of just that. Sorry. Okay. So this is the prototype implementation. We have some fixed examples that here just so that you could try and see what it does. I'm going to try to show you the infinite lists, which is basically the repeat function, two forms of it. So the first one is a cyclic repeat where we just reuse the same cell every time. So getting more values out of this infinite list would not cost us anything. Let's run the analysis to see what it says. Sorry. Okay, so the output is a bit verbose. The two important parts here are the fixed cost on the turnstile that you would see on the type rules. That says a cost of 4. I'll get back to this cost in a while. And the result of repeat 1 would be an infinite list of ones, right? And here in the type, what we have is a type of lists where every annotation is 0, which means we could taking the tail, for example, of this infinite list would cost us nothing. So and the fixed cost is just about these LEDs that we have here. When so each LED repeat costs 1. This LED repeat prime, another one, 3 here, and then after applying repeat 1, this LED columns would be also costed, and that's where this 4 comes from. So if we try to use the other repeat prime, which does not reuse the same heap cell, it really builds all the ones as we ask for it, right? Well, first of all, in the fixed cost, it would be different, but here in this example, the important part is this cost here in the tail of the list, saying that for each element that we would get from this list, we would have to pay a cost of 2. Right, so I'm running out of time, so I'm going to get back to the slides. Just to conclude, so what we have is the first automatic analysis for costing the lazy allocation with guaranteed worst case bounds. We have with the soundness proof and a prototype implementation that you can try your examples or and check the examples we have there. And for further work, we want to deal with the allocation. So in this work, we are measuring the total number of allocations, not heap residency, for example. And we could just extend this some other ways. Nonlinear cost bounds, which is the work that's been applied to the strict case. And maybe why not to Haskell. Thank you.
Thank you.